Good day. I am pleased to be here on the virtual conference on chemistry and its applications 2026, presenting our work entitled Comparison of the Electrochemical Behavior of Biochar Obtained from Cocoa Husks in Sulfuric Acid and Sodium Sulfate Electrolytes for Applications in Electrodes for Supercapacitors. Thank you for your invitation, and let me begin. Recently have been reported that globally food waste accounts for 1/3 of global food production in 931 million tons of wasted materials annually, according to the latest United Nations Environmental Program report. And this is about the 8 to 10% of global greenhouse gas emissions, as much of it ends up in landfills, in addition to including an economic cost estimated of around $900 billion annually, according to the FAO. So that means that bio-waste is a growing, significant problem that must be addressed for new generations. There are many proposed ways to recycle, to use bio-waste. For instance, the most common is for compost or for soil nutrition, maybe the creation of bioproducts, also for land reclamation and erosion control. But mostly and most interesting is the use of bio-waste as subproducts as animal feed, and lately for biogas for renewable energy. So motivation for this work. Mexico is one of the largest agricultural producers in the world, and mostly in North America. Mexico is located in North America in the south of the United States, and commonly produces products like banana, sugar, palm, cocoa, corn, lemon, orange, pineapple, pumpkin, among many other agricultural products. Because of that, Mexico produces also a large amount of bio-waste. For instance, some reports estimated that Mexico produces between 50 to 75 million metric tons of waste. That means a very large concern about what to do with this waste. Because of that, the aim of this work is to propose a different way to use agricultural waste, in this case from the cocoa husk bio-waste that is very common in the south of Mexico, particularly the state of Tabasco. Starting with the collection and treatment of the husk, we pretend to prepare biocarbon that can be used as an active material in supercapacitor. Maybe in this way to decrease, to lower the prices, the costs for supercapacitors, and at the same time to start an interest in developing technological materials here in South Mexico. To obtain carbon, all traces of pulp and impurities were removed from the cocoa pods, which were then washed with ionized water and ethanol in ultrasonic bath. The material was then dried in an oven at 90 degrees C for 48 hours. Then, a system of crucible arrangement with silica sand was used to restrict the entry of oxygen into the system. 10 milligrams of dried cocoa pods pieces were placed inside a 30 milliliter alumina crucible, covering the empty spaces with silica sand. After this, a heat treatment was carried out at 1000 degrees C for 2 hours. Finally, the sample was recovered and ground until a fine powder was obtained. And after that, the electrochemical tests were carried out. The biocarbon obtained was characterized by several methods, Particularly XRF and X-ray diffraction analysis were carried out. Um, Also, Raman spectroscopy were carried out, and functional characterization was carried out by cyclic voltammetry on a potentiostat using electrolytes of sulfuric acid and sodium sulfite. And finally, a supercapacitor was assembled in a CR2032 shell as shown. As a result of chemical composition analysis by XRF, we obtained that a predominance of carbon is being observed in the material with the presence of 93% in weight. This is because cocoa pods are composed mainly of cellulose, hemicellulose, and various carbohydrates in the form of fiber and their structure. Additionally, elements such as potassium, calcium, and phosphorus were observed, which is currently observed for this kind of soil. XRD shows some common patterns related with pyrolytic carbon, but also some additional phases like calcium carbonate, potassium oxide, and some calcium phosphides, which is that is commonly found in some of these agricultural waste treated at very high temperatures. The results of Raman spectroscopy have revealed the presence of D and G bands around 1350 to 1400 cm and 1589 to 1700 respectively. These bands are characteristic of carbonaceous materials, and in this case is density of the D band which is characteristic of disordered carbon is greater than the G band, which is characteristic of graphitic domains, indicating a predominance of amorphous carbon due to the IDIG ratio. In this case is 1.07. The D plus signal, also characteristic of disordered carbon, is also present. Additionally, D3 signal corresponding to carbonaceous material according to the Seelke model and vibrational L modes and AG symmetries resulting from the presence of carbonates in the analyzed materials as observed in the XRD results. These results confirm that the information we shown in the X-ray diffraction analysis, because bands associated with carbonaceous materials with disordered or amorphous structures have been identified, favoring the formation of poles. The behavior of the material obtained in cyclic voltammetry is observed here. These analyses were carried out at different speeds, 60, 50, 40, 30, 20, and 10 millivolts per second in two different electrolytes, sulfuric acid and sodium sulfate. In both cases, the change in the area of the quasi-rectangle can be observed as the scanning rates decrease. This affects the specific capacitance obtained because the ions have more time to interact with the working electrode as the time decreases. This material predominantly exhibit electrical double-layer capacitor mechanisms, which are characteristic behavior based on ion exchange at the electrode-electrolyte interface. Furthermore, the material behaves as a resistive capacitor, which produces a wider angle in the shape of the quasi-rectangle. Comparing the results for the two different electrolytes, it is noticeable that the sulfuric acid electrolyte allows for a larger quasi-rectangular area due to its higher ionic conductivity. smaller ion size, and proton-driven conduction mechanisms, resulting in a higher specific capacitance. Using the equation to calculate the specific capacitance, is possible to calculate the specific capacitance for this material, and it was calculated in sodium sulfate and sulfuric acid as 30.7 farad per gram and 47.5 farad per gram, respectively. The analysis by electrochemical impedance spectroscopy in both solutions allow for a better understanding of the electrochemical processes that explain the electrode performance. To this end, equivalent circuits were modeled initially, including two clearly differentiated resistances, one associated with the electrolyte resistance and the other with electrolyte interfacial resistance. This highlights the combined influence of ion transport in the medium of the kinetics and the kinetics of charge transfer at the electrode-electrolyte interface. Subsequently, a constant phase element was found to present a non-ideal capacitive behavior that explains the angle present in the graph. This is attributable to the structure of the carbonaceous material derived from biomass, such as cocoa pods in this case, as well as to the non-uniform distribution of electroactive sites due to its amorphous structure. Despite the predominance of the ADLC mechanisms, the parallel connection of the constant phase element with a resistor suggests simultaneous capacitive and faradic processes. These faradic processes may be due to the presence of carbonates, phosphates, and oxides in the material composition. Finally, the representation of a Warburg element in both circuits illustrates the diffusive process of electrolyte ions within the porous structure of the electrodes. This is characteristic of carbon-based electrodes used in supercapacitor-type energy storage systems. As conclusions, we can remark that carbonation by carbon was successfully synthesized from unmodified cocoa husks via low-cost carbonization in a reduced air atmosphere. XRF and XRD confirm key ash compounds, for instance, calcium carbonates, calcium phosphates, and potassium oxides. While Raman spectroscopy verified a highly disordered, mostly amorphous carbon structure with small graphitic domains, the cyclic voltammetry demonstrated specific capacitance of 30.7 and 37.5 farad per gram in sulfuric acid and sodium sulfate electrolytes, respectively, driven primarily by EDLC mechanisms. Furthermore, electrochemical impedance spectroscopy and equivalent circuit fitting resolved internal resistances and capacitive contributions, highlighting cocoa pod-derived biochars as promising supercapacitor electrode materials. These are the references. Thank you very much for your attention.